Hello, everyone. Welcome to the session of bugs and repair. So in this session, we have 6 talks, including 1 technical research talk, 2 software engineering practice talk, 2 journal first talk, and 1 new idea talk. So I am Yin Fei from Peking University. I'm the session chair. So if you have any questions regarding the presentations, please ask them in Crowder, and I will vote the questions if you prefer to be asked, and I will pick from Crowder. So the first talk will be given by Xindong Zhang. He will talk from Alibaba. He will talk about the prefix, a large-scale patch recommendation by mining defects patch pairs. Yeah, Xindong, please. Xindong, you are mute.
Oh, could you hear me? Right. Oh, okay, perfect. Hi all, this is Xindong Zhang. Thanks to ICSI committee, thanks Xiong Forum for organizing this session. Let me introduce our work on patch recommendation. This is joint work of Alibaba Group, UT Austin, and Nanyang Technology University. So patch recommendation is the process of identifying errors in software systems and suggesting suitable fixes. Automated patch recommendation can significantly reduce developers' debugging efforts and the overall development costs. Moreover, it can improve software quality and system reliability. We conducted a preliminary study of the usage scenarios of patch recommendation techniques within the company and empirically analyzed the characteristics of the company code base. We found multiple challenges. First, we need a general solution for diverse applications. Second, test cases are usually insufficient. Some generate and validate approaches which rely on test cases may hardly apply to entire code base. Third, we lack patch labels. Labels from SCZ algorithm have noises, and manual labeling is impossible on such a large data set. Finally, practical usage requires that the techniques should be highly responsive and have low false positive rates. So we propose our solution, Prefix, a pragmatic approach targeting large-scale industrial code base and making recommendations based on previously observed debugging activities. It automatically mines bugs and fix templates from historical code changes using generic features, which doesn't rely on patch labels and can handle diverse applications. So our solution is independent of test cases, and we use developers' feedback to validate and improve. As for practical requirements, we can scan and recommend patches within milliseconds. False positive rate is 22% also, and we are improving it by developers' feedback. Here is the specific introduction to Prefix approach. We extracted sample benchmark set, which includes over 10,000 software projects spanning over 15 million commits and 30 million files. For the offline patch discovery part, it consists of 3 main steps. The first step is defect patch pair extraction. We made use of keywords in commit messages to extract bug fixing commits, like fix, bug, or even similar words in Chinese. And we observed more than 3/4 bug fixing commits have such pattern. Remove bug snippet and insert patch snippet. According to it, we extracted defect patch pairs. After extraction, these pairs still contain lots of noises. We made some adjustment. Firstly, we set a threshold on the number of files modified in bug fixing commits to filter out most multi-purpose commits. Secondly, we confine the scope of defects and patches to be within a single method. To further reduce noises, we apply clustering techniques to cluster similar patch behaviors. So the next step is clustering. dbScan is our choice for clustering, and the combination of Livingston distance and Jacquard distance is applied for similarity comparison. For sake of efficiency, we made 3 major improvements. First one is use same hash plus KD tree in the mapper period. Secondly, we made some normalization to snippet strings. Finally, we exploited API sequencing information. 2 snippets can be compared only when they share at least one same API call to avoid most comparisons between 2 totally irrelevant defect patch pairs. So totally we save 95% running time. The final step is to extract defect and patch templates from clusters, which makes developers easier to understand. As for the online part, Preface will scan developers' code change when they commit code review. If defect templates are found, patch will be recommended on code review system, and the developers can give us feedback for further improvement. So you might be curious about what kind of patches that our solution clustered. So here, let me show you some examples. I randomly sampled 50 patches found by Preface and made classification on them. They can mainly be divided by 3 classes. The first one is API modification, like the modification, addition, or deletion of the parameters. Validation check account for 26%. It includes non-pointer exception check, boundary check, and so on. API wrap class is out of our expectation. This kind of patch recommends developers to use already existed utility functions instead of implementing it again to avoid unexpected defects, which indirectly improves the code quality. Finally, we talk about results. The false positive rate is 22% also, and it is supposed to be reduced gradually. We interviewed some developers with 2 questions. The first one is the patch suggested by Preface valid? If so, would you like to apply the patch? And the second question is, would you like to use Preface during code review? The majority of interviewees said yes. The offline patch discovery part costs 5 hours or so, and it can do patch recommendation within milliseconds. Preface has been deployed on code review system in Alibaba internal platform, code platform for 1 year so far. And it now can be also used on CodeUp on Alibaba Cloud. In conclusion, we present Preface, a patch recommendation technique designed for large-scale industrial code base. It is feasible, unsupervised way to find patches. And theoretically, Preface is language agnostic, so we plan to apply it to different languages in future. Thank you for your attention. Questions are welcome.
Oh, thanks, Xindong, for the presentation. So here's a question. When you say you confine the scope of the defects and the patches within a single method, do you mean that the patches in your dataset change only one method?
We just attempt to make our model be simple but applicable to the most common cases. And this is one way to confine the patches and defects in one single method, but also you can just extract defect and patch pairs from diff chunks, not within methods. Both approaches are available, and they have just trade-off between precision and recall. Because if you confine the scope in method, you may lose some recalls, but the precision might be higher.
Okay. I do have another question that you mentioned the precision in your talk, but how about the recall? Like proportion of bugs you can fix among all the bugs?
First, to be honest, the recall rate is hard to evaluate because you don't know how many defects exactly in the code. Yeah, to be honest, the recall rate, I think it would be pretty low because it only can cluster similar patch behaviors in the historical code change. So some defects may not be detected by our approach. But our pursuit is to make our false positive to be low and we don't want to disturb our developers or our platform.
Okay. There's another very quick question. Can this technique apply multiple line changes to fix a bug?
Sorry, pardon. What Chinese?
Can your patch generated change multiple lines, more than one line?
Yeah, sure. We use the code clone techniques to detect and make patch. As you see, when we extracting defect patch pairs, we just group the deleted lines and the inserted lines as defect snippet and patch snippet. The snippet can be multiple lines.
Okay, since we're running out of time, thank you very much, Xindong, for the presentation. Yeah. So the second talk will be given by Kui Liu. Xindong, could you please stop sharing and let Kui share? Yeah. So the talk, so Kui Liu is from Nanjing University of Aeronautics and Astronautics. The title of the talk is on the efficiency of test suite-based program repair, a systematic assessment of 16 automated repair systems for Java program. So, Kui, could you please share your screen and start the presentation?
Thanks, Yinfei. Hello, everyone. Can you see my slides?
Yes.
Okay. Hello, everyone. This is Kui Liu. Today, I'm going to present our recent work that is about the efficiency assessment for automated program repair systems. In the literature, research publications about automated program repair are increasing year by year since 2009. Generate and validate automated program repair is one of the commonly studied domains, which consists of three basic processes: localization, patch generation, and patch validation. In the community, researchers mainly focus on proposing new patch generation approaches to boost program repair. By looking at the repairability across time, indeed, the number of bugs that are fixed by different tools over the years is increasing. And except proposing new patch generation approaches, other domain has been explored to boost program repair, such as the overfitting patches generated by API tools. Better test cases for better program repair. Can API tools fix hard and important bugs? The bias caused by fault localization configurations and the overfitting benchmarks for API systems. So we wonder, how about the efficiency for API tools? To evaluate the efficiency of API tools, the number of validated patches and time costs have been utilized. For example, this table shows that the time cost for validating each CROI patch is almost 2 times for validating each chat patch. It implies that the time cost for validating different patches for different programs are not consistent, even for the same API tool on the same machine. So it is challenging to define a generically suitable time budget for repairing bugs. We further checked the CPU time costs for compiling and testing defects for their programs on 2 different machines. These results show that the time costs for compiling and testing different programs on different machines are significantly different. So time cost is not a reliable metric to enable reproducible and comparable experiments on the efficiency of program repair. Therefore, we propose MPC as the metric for efficiency, the number of generated patch candidates when the first valid patch is found. to assess the efficiency of API tools, we use 4 different criteria to select API tools from the community: availability, executability, configurability, and standalone. In this way, 16 different API tools are selected from the community, which are further grouped into 3 categories: heuristic-based program repair, constraint-based program repair, and template-based program repair. This experiment is conducted with the commonly used defects project box. To eliminate the bias from localization, all of the 16 API tools are configured with GSOTA 1.7.2. If a patch generated by an API tool is identical or semantically similar to the developer's patch, such a patch is considered as correct. In this study, the NPR scores are counted with 3 kinds of patches. Nonsensical patch. This kind of patch cannot make the patched buggy program pass the compiling process successfully. The second kind of patch is about in-process patch, which cannot make the patched buggy program pass some test cases. The third patch is valid patch, which can make the patched buggy program pass all test cases successfully. First, we investigate the patch generation efficiency of with MPC scores. This result shows that we first noticed that if API tools consider some code change templates, they can fix more bugs, but they also generate more patch candidates. If API tools use the constraint solving approaches, they can yield less patches, although they need some more resource for the patch generation. We further comparing the difference for the nonsensical patches and in-process patches. We first note that some API tools, they can avoid generating the nonsensical patches. We also noted that if API tools consider more templates, the more nonsensical and in-process patches will be generated. For the template-based API tools, if the templates are specialized, they will increase the efficiency by generating less nonsensical and in-process patches. We further comparing the differences of MPC scores for between before and in-process patches and before correct patches. This result shows that a correct patch can be more efficiently found than a process patch. So based on this finding, we conducted another experiment for the API performance by setting MPC impossible threshold for the patch generation. In this experiment, we found 14 of the 16 API tools, their ratio of generated process patches to be correct is increased by setting such a threshold. Finally, we also investigate the impact of photolocalization noise for the efficiency by setting another experiment. We give all the 16 API tools as given with the buggy positions. By comparing with the previous experiment, we found that given API tools with buggy positions, the API tools will generate less patch candidates to fix every bug. So this results show that false positives of photolocalization have a significant impact on the repair efficiency, and the accurately locating the bug can enhance such efficiency. Our work is about the efficiency assessment for API tools. All the results are publicly available from in GitHub. Thank you for your listening. Questions are welcome.
Okay. Thanks, Kui, for the presentation. So yeah, I have a question is that, do you have any recommendation for the future program repair tools based on this study? What should, if I'm a company, I want to develop my own API tool, or how should I do?
I think first thing is about the efficiency, because currently for different tools, they're always setting a time limitation for their experiment. Like some tools, the limitation is set in 3 hours, but other tools are setting in 5 hours. So in our experiments, we show that the time limitation is not so fair, it's biased. So maybe in the future, for the time limitation setting, they can use another way, like the number of pitch candidates. If there are almost 1,000 or 10,000 patch candidates are generated, the bug is still not fixed. Then they can stop the fixing process, but do not using the time limitation. As we showed that time cost for comparing and testing programs are different. So for different programs, even on the different machine, so it's already biased. Maybe the number of patch candidates is somehow more fair than the time limitation.
So, okay, I guess that's, I probably asked the wrong question. So I think a more proper way to ask is, for academic researchers, what does the findings imply? How should we change our practice in future? I think you already mentioned one that's about the bias in evaluation. Do you have any other implications, recommendations?
You mean from
the integral study, from the findings? What's the implications? Could you talk about? Yeah.
I think it's about the maybe about this one. I think this one maybe if I'm interested in our experiment, we found that if we do not set any, just use the time limitation, do not set any threshold for the NPC scores, they can have another correctness ratio. So if we setting NPC threshold, so their correctness ratio can be improved.
Okay, I think there's another question that's very related to the previous one. What's the main takeaway points based on your study? Should the researchers focus on improving the test suite?
I think if researchers should focus on how, first thing is focus on how to accept to fix more bugs. Second thing, they also focus on improve the efficiency, because the automatic program, the target for automatic program repair is for improve the efficiency for fixing bugs. So in the future, the efficiency should be a target for API tools.
Okay, thank you very much,
Thank you
for the presentation. So, yeah, please stop sharing. So the next talk will be given by Steve. Steve is from the Colorado State University, and the title of his talk is Sequencer.
Thank you. Let's get sharing here. Yes, I'm Steve Kamrush from Colorado State University, and I'll be presenting Sequence to sequence learning for end-to-end program repair. This is originally published in Transactions on Software Engineering. And so what we focus on is one-line commits. One-line commits are a common bug fix type representing about 10% of the commits in GitHub. And SequenceR trains on these type of commits and learns how to replicate them and recommend them for patches. So for example, we can learn call deletion, where you might have 2 calls to 2 different methods in a row, and the correct fix is to delete one of the 2 calls. Another potential fix is argument addition, where you have a method call and the correct fix is to add a new argument. And in Java, this actually calls a different method altogether, different implementation of the method. So SequenceR can learn these types of transformations as well as a variety of other types that are detailed in our paper. So the sequence to sequence model was originally developed for human language translation. And here we show the X sentence being input to the model token by token. and the desired result is the Y sentence. So you're translating from a series of tokens in one input format to another to an output format. The hidden boxes are computing an embedding for the sentence that's being created. And there are learnable weights that take into account the current state as well as the current input token. And then the output also has learnable weights so that it learns which tokens of the target language are being created. So for sequence R, we're translating from buggy code to fixed code. So in the original code shown on the left, we have a full class with multiple methods in it. There's a method called increment, which has a bug. And through fault localization techniques, which we don't cover in this paper, you might identify a buggy line. And what we do is we abstract the class. We keep all the methods, but we delete the internal code from any of the methods that don't have the bug. And then we identify the buggy line with a start bug, end bug token. So that's basically what's input to our neural net. However, we also deal with the unlimited vocabulary problem where people might name variables or methods any arbitrary set of characters, and those get replaced with unknowns if they're out of the learned vocabulary. But the position of those unknowns still provides a context, and the original tokens can be used in the output patch. And we'll talk about that in later slides. So the way that the training and use model works is we've mined human commits from GitHub, and looking at single line commits, we create the buggy context abstraction for the pre-commit code. And then the fixed line that the human checked in is our training target. So we update all of the parameters using backpropagation to get a sequence to sequence network to create the patched line. So it's getting the full class, the buggy context abstraction as input, and it's just creating a fixed line. So now in the use model, you might have a failure in your project, and fault localization is used to identify which line might the failure be at. Sequence R will produce multiple patch proposals, which can then be evaluated using the test suite, the same test suite that was used for the fault localization, and then patch validation can be done. So some details on our model. We have a modern encoder-decoder structure. The encoder uses LSTMs to build up an embedding of the abstract buggy context, and the decoder also uses LSTMs to create a sequence of tokens for the predicted line. They're connected together. The encoded LSTMs initialize the decoder LSTMs to give them the interpretation of the context. And then the copy selector can be used when the decoder is in a particular state. It might decide that based on a state from the input, it should copy the token. So this is how tokens from the input can be copied to produce the predicted fixed line. And so how that works for us is if we look at inputs with no context, so here we're just taking a buggy line and trying to create the fixed line. So we have no context. 50,000 word vocabulary without the copy mechanism. The first guess from the network, beam size 1, is 55 correct out of 4,700. If we go to beam size 50, so we allow the network to make its 50 best guesses on what it's learned, we get about 4 times better result. But if we switch to the copy mechanism, so now we have a smaller vocabulary, which means we're using a lot of unknown tokens that the system has to learn how to copy, it does a lot better. Now we get up to 826 correct. And then if we put the abstract buggy context in, which allows for the full method and most of the class to be available for context, but also for copying of identifiers, then we get up to our golden model, 950 correct out of 4,700. Now, defects for J is a great data set to use for evaluating these kinds of tools. If we look at the total number of bugs and defects for J that can be fixed with a single line fix, that's 75. And we generated patches for 58 of those bugs, of which 53 of the bugs had a compilable patch. The number of cases where the bugs passed all test cases was 19. So here's our plausible patches. And then 14 of those 19 were correct. So in our mind, that 19 number is pretty key because everything down to the 19 is automated. It could have been running overnight or in the background. When the system finds a potential fix, it'll identify for the users that there might be a patch here. The human will find that 14 of them were correct, and the 5 that weren't correct are potentially indicative of an opportunity to improve the test suite. So all of those 19 patches are kind of interesting from a software engineering perspective. So in the end, SequenceR is the first system that generates compilable test verified patches based on a neural machine translation. And we found the correct patch for over 20% of our test data and 14 out of 75 bugs and defects for J. Thank you.
Okay, thanks, Steve, very much for the presentation. Unfortunately, we are running out of time, and I see some questions in Clouder. You can just ask the authors where the chat channel over Slack or over Clouder. So let's move to the next presentation. The next speaker will be Jie Zhang from UCL UK, and the title of his talk is a study of bug resolution characteristics in popular programming languages. Yeah, Jie Zhang, please.
Sorry, can you hear me now?
Yes.
Okay, great. Hello, everyone. I'm Jie Zhang from UCL. I'm currently a research fellow. So welcome to my talk. And today I'm going to introduce our TSE work on a study of bug resolution characteristics in popular programming languages. So there are a lot of programming languages, and it's very important to learn more about them. In particular, their bug resolution characteristics. Because, for example, developers, they really spend a lot of time dealing with bugs. And according to our survey, over half of the developers, they would consider bug resolution effort as a factor for language selection. And for researchers, we also spend a lot of time dealing with bugs. We do automatic program repair, we do mutation testing, and also bug effort prediction. And these research activities, we may need different solutions for different languages. However, currently there are a lot of debates on the bug resolution characteristics among different languages. So take Python, for example, some people think that bugs in Python, they are easy to handle because we know that Python code is quite easy to read and understand. But some other people may think Python 2, there's no static typing, but even in Python 3, static typing is not mandatory. So this issue may lead to more bug handling effort. So in this work, we would like to do something to shed light on these kind of debates. And we want to know, for projects constructed from popular programming languages, which projects they have more correlations with longer bug resolution time and larger patch sizes. So I would like to strengthen that what we want to do is correlation analysis study instead of causal analysis. So to get the answer to this question, we conduct a large-scale study using the data that we mined from GitHub projects. And we use different measurements to measure the bug resolution efforts. For example, we measure the lines of code for the patches and also the number of files that you need to change when fixing a bug, and also the bug resolution time. So we use different statistical analysis approaches. The reason is that we want these different methods to mutually validate each other. So if different methods lead to consistent conclusions, these conclusions would be more reliable. And also we have different levels of analysis. We have the project level analysis where each analysis subject is a project. We also have the commit level analysis where each analysis subject is a commit. So we choose 10 popular most popular languages based on some language rankings. And we also classify these languages into different categories because we also want to study the differences among categories. So while we mine the bug resolution commits, here are some interesting findings. We realize that those previously widely adopted keywords like issue, mistake, and fault, they only have 30% precision when finding the bug resolution commits. So that's why instead in this paper, we only use fix and bug, which means when a commit message contains both fix and bug, we would think this commit is a bug resolution commit. And this would have a 95% precision. Okay, so next I will quickly go through our results. For the first research question, we want to compare the languages. So it's quite interesting that when we focus on the bug resolution lines of code and also the number of files, we could see that Java and C#, these two languages, they always rank first among all the languages. And this means that in our corpus, projects written in Java and C#, they have notably higher bug resolution size than the other languages. So this conclusion is not surprising because we all know that Java and C#, they are quite verbose, right? So what about the bug resolution time? So it's also interesting to observe the consistent conclusions from different analysis methods. That is, we observe that Ruby language always rank first among all the languages, which means in our corpus, projects written in Ruby consume notably higher bug resolution time than the other languages. So when it comes to the second research question, we compare different language categories. So compare the dynamic and static languages, also weakly typed and strongly typed languages. And our conclusion is that strongly and statically typed programs in our corpus have larger patch sizes, and dynamically typed languages tend to consume longer bug resolution time. Okay, so here are some interesting implications for researchers. So when we do automatic program repair, our findings indicate that different languages, they need different patch sizes and also search space. So when we do mutation testing, we want our mutants to simulate real faults. And based on our findings, some languages, they may need more code transformations to simulate real faults. And for bug effort predictive models, when we do the prediction, we may need to consider the differences among languages. And for all the automation research, and I think software engineering researchers really like to do automation part. Actually, languages that correlate with more bug resolution time may deserve more research support. Okay, that's all for my talk. Any questions are welcome. Thanks.
Okay. So I have a question. So when you mentioned the patch size, how do you measure patch size? Do you count the number of tokens or do you use other kind of measurement?
Yeah, for patch size, we measure two types. One is the lines of code. One is the number of files. So,
okay.
Yeah, we think that, for example, of course, the more lines you modify, the larger the patch is. And
okay, but I think the lines of code, like in some functional programming language like Haskell, you tend to write everything just in one line. So the line is usually longer than perhaps in imperative languages. Do you consider this kind of issues?
Yeah, I think that's a very good question. So we didn't study languages like Haskell. I think for the languages that we study, most I think they just obey the rules that, for example, each line has one statement.
Okay. Yeah, I think that's pretty much the time. So thanks, Jay, again for the presentation. So let's move to the next one. Next one will be given by Jay. Could you please stop sharing? And
okay, thanks.
Yeah. So the next one will be given by Shuyue Li from Xi'an Jiaotong University. The title of her talk, Shuyue, could you please start sharing? The title of her talk is Automated Bug Reproduction from User Reviews for Android Applications. Yeah, Shuyue, please.
Okay, can you hear me?
Yes.
Okay. Okay, hello everyone. I'm Shuyue from Xi'an Jiaotong University, and the work I will present today is named Automated Bug Reproduction from User Reviews for Android Applications. So our motivation is very simple. Negative user reviews, especially the bug-related ones, can influence the reputation of an Android application. And meanwhile, the bugs really influence the user experience. So the app developers must fix the bugs mentioned in user reviews as soon as possible. And the very first step is bug reproduction. So what we expect to do is to automate this task and help developers or testers in their work. It sounds very useful, but the question is how? So first of all, we inspect more than 3,000 bug-related reviews from Google Play, and we find out two major challenges to accomplish our goal. The first challenge is that the user reviews are quite noisy. And secondly, it is also difficult to leverage very limited information in user reviews to reproduce bugs. I will show two simple examples here. Firstly, there are many noise in user reviews, such as misspelling, repetitive words, and also very much unrelated information to the bugs. For example, the users may write their complaints or suggestions in user review, so these are the noise. But the useful information for bug reproduction in user reviews are very limited. For example, in our dataset, we find that rare user reviews specify the device or the Android operation system version on which the app runs. And the information that the user provides is very limited. For example, the users tend to only describe the last action or the last state of the app before a crash happens. So to solve these challenges, we design our approach and implement a tool named the reproduction. There are two phases in our approach: user review processing and guided search. In user review processing, we aim to extract information or informative words from the original user review. We identify two kinds of important information for bug reproduction. The first one is functionality description. We find that these words are frequently occur in one app's user reviews, but rarely occur in the other apps. So we use token frequency analysis to extract these kinds of words. And the second kind of informative words is GUI actions and GUI components. We find that users tend to describe GUI events with two grammar patterns: verb objective structure and the passive nominal subject structure. So we use grammar analysis and the dependency tree to get this kind of information. There's a simple example here. We can see the original user review says it crashed when I access r/or. So there are diverse words of GUI actions and the GUI components. And the original, that these words can disturb our later grammar analysis. So first of all, we normalize the words of GUI actions and the GUI components. And we can see here we normalize this sentence and it became crash when I click button. And then we can use a dependency tree to get our informative words. And the results of the user processing, we get informative words, and these words will serve as the guidance in our guided search. So we guide the search at each step with the information from user reviews, and we adopt the depth-first search strategy, which is widely used in Android testing. But the GUI space of an Android application is very huge and unbounded. So for efficiency, we designed two major techniques for our tool. And the first one, at each step, we rank GUI components by user review. There are some key observations here. We find that GUI components are usually short, so the words they contain is very limited. And the different components in one app share many same words, so their similarities to user review are usually close. And at the same time, there are a lexical gap between user reviews and GUI components. So to efficiently rank these GUI components, we combine word embedding and frequency analysis. And the second technique is one-step exploration. This is designed for an observation that in our exploration, we find that there are many circumstances where the scores of GUI components on current screen are all zeros. So the ranking is useless and our search may degenerate to random search. We do not want to choose one component randomly in this circumstance. So we enhance the information of a GUI component by the screen triggered by interacting with it. So we design this one-step exploration and we interact with one component and it triggered a new screen and we recalculate the ranking result with the new information and then we re-rank our GUI components on current screen. Here's an example we can see in this picture. In the left screen, there is no similar component with the original user review, which says add a photo from camera. But when we click with this button here, we can see it triggered a new screen and it has a high similarity with the original user review. So we can confidently click this button now. And I will quickly show our evaluation result. For the first question, we want to see whether our tool can really reproduce bugs from user review. So we collect 17 popular applications from Google Play, and our tool has about 70% success rate. And for the second research question, we want to see how much time our tool spent on bug reproduction, and we compare our tool with human participants who try to reproduce bugs manually. And we can see our tool spend more time than human, but the time is still acceptable. We also find that human also spend more time on the crashes that our tool fails to reproduce. And for the third research question, we want to see the effectiveness of our two major techniques, one-step exploration and user review processing. And the results show that these two techniques are both useful for our efficiency of our tool. And finally, we also conduct some failure case study, and there are 4 major failure causes here. Since time is limited, I will not explain them one by one. I will show only one example here. The major cause of our failure is the first cause, comprehension, the lack of comprehension of natural language in user review. And here is a user review where the user says the app crash if you have more than 4 levels of sub-account. So this description does not directly link to any GUI action. So our tool failed to reproduce this bug. And to summarize, our team proposed a automated bug protection tool from user reviews on Android platform. And we hope our tool can help many developers or testers in practice. So that's all of my report. Thank you.
Okay, thanks, Suya, for the presentation. So I see some questions on Slido. So the first one, does the method support multi-languages? If so, how did you extract semantics from different languages?
What language? You mean Chinese, English, right?
I think it should be more multiple programming languages. So not if not just Java, if other kind of programming language.
Currently, we only support Android bug protection because we search on the GUI surface of Android applications. So all the search strategy are designed for Android GUI screens. So yeah.
Oh, on a second thought, it might means that different natural languages. Do you support multiple languages like Chinese and English?
We currently only support English. Yeah.
Okay. So another question is, when comparing with human reproduction, how knowledgeable of the apps is the human involved in trying to reproduce the crash?
Okay, the human we ask for bug reproduction are all the students in our school. So they only firstly use the app for 5 minutes, and we will then ask them to reproduce the bug. Yeah.
Okay, I think the question is actually asking that in what point the tool outperform the humans or be outperformed by the humans?
It actually not outperform the human performance. Yeah.
I mean, so that's by quantitative analysis. So you have some correlative analysis. In some aspects it's better, in some aspects it's bad. Do you have this kind of analysis or no? Not yet.
We didn't. Yeah, we didn't analyze that. Yeah.
Okay. Yeah, I think it's almost time. So thanks to Su-Yue again for the presentation, for the QA. So let's move to the last presentation. So unfortunately, none of the authors will be available for the presentation. So we will just use the recorded video. So this is a new idea paper from Federal University of Silla. And the title of the paper is Chase, Checklist to Assess User Experience in Internet of Things Environments. And since the authors are not available, we won't have a QA session. So yeah, student volunteer, please help play this recorded video.
Hello there, my name is Tiziane Darim. I'm from Brazil, and it's a pleasure to be here today to present for you guys our work
we can't see the video. We only
Chase,
hear the
a checklist to assess user experience in IoT environments. My co-authors and I are from the Federal University of Ceará. In a smart objects may operate in multiple contexts. Each time someone interacts with Hello there, my name is Tiziane Darim. I'm from Brazil. And it's a pleasure to be here today to present for you guys our work named Chase, a checklist to assess user experience in IoT environments. My co-authors and I are from the Federal University of Ceará. In an IoT environment, smart objects may operate in multiple contexts. Each time someone interacts with a smart object, the success of this interaction may be more related to personal characteristics and the context of use than with the technology itself. Because of this, and because IoT systems are rather complex, every time we evaluate IoT quality in use, we should consider evaluating it from the perspective of the user. At this point, you may ask, isn't this type of evaluation necessary for all types of systems? Yes, absolutely. But in IoT systems, we have to consider some specific challenges. For example, we have an environment with multi-platform interaction and interconnection between devices with different interfaces, with different capabilities. We have also two different types of interactions. Human-thing interaction, which is interaction between users and smart objects. And also we have thing-thing interaction, a type of interaction among smart objects, and both affect the user's experience. Besides, we also have a less tolerant user because they really expect that smart objects work as well and as efficiently and as quickly as their everyday objects. Well, cutting to the chase, our point is that in IoT systems, to deliver a good quality in use, we have to actually observe users in user testing and go a little beyond what traditional UX measurements can give us. We propose Chase, which is a checklist, an observational tool to be used during user tests, and that will help you to disclose some of the problems that may affect the user's experience and focus on how the IoT systems affects the user behavior. To come up with the current version of Chase, we basically follow the four-step process that I will quickly summarize for you right now. First, we did a literature review, and we were able to identify some criteria on how to evaluate IoT systems regarding UX aspects. Then we created an initial version of this checklist, and we engaged potential users and experts in reviewing it thoroughly. Then we updated the checklist and applied it in a real context of use with different evaluators, so we could evaluate the quality of the checklist items and concreteness, applicability, ease of use, and so on. The final version of Chase has 26 checkpoints divided into two categories: human-thing interaction and thing-thing interaction. Human-thing interaction contains items to evaluate the interaction that occurs between smart objects and the user, and thing-thing interaction contains items to evaluate the intercommunication between smart objects in order to provide the user with a service. We have also 5 modules: general aspects of UX, which is exclusive to human-thing interaction category, and it's intended to evaluate user satisfaction, user control over the IoT aspects of the application, and the environment, the user's perception of utility, and so on. Context awareness is in both categories, and it comprises items on how the user context affects the smart objects and vice versa. And programmability regards the variety of programmable behaviors that smart objects usually offer the user. Finally, we would like to invite you guys to try Chase and let us know what you think about it so we can keep improving it. It's ready to download and apply in your user tasks with IoT systems. Thank you so much for your time and attention. If you have any doubts or questions, please contact us. Thank you.
Okay, thank you very much for playing this video. So this is we are now at the very end of the session. Let's thank all the presenters, all the audience, and the virtualized team to make all this session happen and success. Thank you. Okay, so some notice: if you want to talk to the presenters of the session, you can look for the presenters of the session in the lobby's video chats during the third hours if you want to ask them more questions. Also, don't forget to visit the poster and demo today in the third hour by going to the Clouders exhibit hall and joining the presenters in their own video chats. Okay, thank you and enjoy the rest of the conference.
Bro, nice job.
Hello, everyone. Can I start it? Okay. Hello, everyone. Welcome to XC 2020 Pacific 12 sessions. I'm Taek-soo from Samsung Research. Glad to see you. Today's topic is testing and debugging, one of the most important research topics of software engineering. 6 papers are waiting for us, 2 from SIP track and 4 from Journal First. If you have any question during a talk, please ask the presenter via Slido. Okay, let's start the session from the first presenter, Ms. Rebecca Chan of Facebook. Hi, Rebecca. Please open the session with your talk.
Hello, thank you for the introduction. I'm going to share my screen. Okay, is my screen share working correctly? Okay. So hi everyone, I'm Rebecca. Today I'm talking about our paper, Debugging Crashes Using Continuous Contrast Set Mining. So this is work done by researchers and engineers at Facebook. So large software companies can receive millions of crash reports. Say you are an engineer trying to resolve a large number of mobile crashes. You don't have enough people to look at individual crash reports, so you bucket these crashes, for example, by stack trace similarity. You then assign each group of crashes to an engineer to debug. Okay, now what? You want to know what distinguishes this group of crashes from the other groups of crashes. For example, do crashes in this group occur disproportionately in a particular country? Or is a particular build version combined with an OS version appearing more frequently in this group than others? To extract insights like this, we can apply contrast set learning, a pattern mining technique that combines statistical testing and tree search to find differences between groups. So in prior work, Castelluccio et al. Demonstrated that contrast set mining can extract useful insights from Mozilla's browser crash datasets. The objective of CSM is to find statistically meaningful differences between groups. A contrast set is simply a set of feature value pairs. For example, OS version equals 5, build version equals 4. For a contrast set X in group G, the support is the percentage of crash reports in group G for which the contrast set is true. A contrast set is interesting to us if its support differs meaningfully across groups. There are 2 conditions for this. First, a contrast set must be statistically significant. Under the null hypothesis, the likelihood of observing set X is equal for all groups. We can test this with the chi-squared test. Second, a contrast set must be large. This means the support of the contrast set differs by a user-defined threshold for at least 2 groups. So we implemented the Stuco algorithm, which casts contrast set mining as a tree search problem. We start by enumerating all possible attribute value pairs in the dataset. For each candidate node, we count the support for each group and examine whether the contrast set is significant and large. Nodes that fail either condition are pruned, and we generate children from the surviving nodes, greatly reducing our search space, allowing us to do multiple hypothesis testing at scale. Now, this is great for categorical features that are commonly associated with crash metadata. But what if we don't have this data? So it turns out for certain classes of crashes, the stack trace is unavailable or difficult to obtain. For example, in out-of-memory errors, the OS kills the app and does not have enough memory to snapshot a stack trace. In these cases, developers must use other features and metadata for debugging, such as the navigation event sequences. Enumerating all possible navigation sequences scales exponentially, so we create a compact continuous representation for navigation logs by extracting bigrams of source and destination modules and encoding them with TF-IDF, transforming navigation logs into continuous features. So now we have groups of crashes with continuous features. Can we take Stuco out of the box and run it? So it turns out that to apply Stuco to continuous data, we first need to discretize the data. In other words, we need to bucket the data into bins. Discretization has several drawbacks. First, it greatly increases the number of candidate contrast sets, since each bin becomes a new candidate contrast set, making computation very expensive. Second, results are difficult to interpret, and this may reflect the choice of your cutoff points more than the underlying data patterns. Third, Any form of discretization leads to information loss, especially at the tails. Now, this is true for real-world data, especially, that is often highly skewed. So this provides the motivation to develop a continuous contrast set mining algorithm. In our paper, we present the first ever application of contrast mining to continuous data without discretization. We demonstrate a 40x speedup over a naive discretization approach during our evaluation on a dataset of 60,000 real-world production crashes. We also provide a formal definition of contrast set quality and uncertainty measures to aid interpretability and actionability of our results. So in continuous contrast set mining, or CCSM, our input is a set of k-dimensional vectors partitioned into mutually exclusive groups. Here, k is the number of continuous features. So in our example, it is the number of TF-IDF embedded navigation module bigrams. A contrast set is a set of continuous variables. For example, newsfeed photo, profile video is a contrast set with 2 bigram features. Now, a contrast set is a deviation if it is significant and large. And in the continuous setting, we use the one-way ANOVA F test to test significance. This is a natural counterpart to Pearson's chi-square test. For largeness, we check the minimum difference in means. In other words, at least 2 groups means must differ by a user-defined threshold. So similar to Stuco, we use tree search and pruning heuristics to efficiently search for child contrast sets. So now going back to our example of debugging using embedded navigation sequences. Say we want to see if feed to videos is a deviation. We first compute the mean for this feature for each group. We then run a one-way ANOVA F test to determine statistical significance. If this passes, we run a second check for largeness using the user-defined threshold, which you can think of as a check for practical significance. We make several additional contributions in our paper, aiming to make contrast sets more actionable and interpretable to developers. So you can see our paper for implementation details and more. So here is where continuous contrast mining could fit into the debugging and testing pipeline at Facebook. After crash groups are bucketed, we would run CCSM in parallel with Stuco, and resulting contrast sets would get ranked and sent to tools that create visualizations and alert developers of the anomalies. We evaluated the execution times of different contrast mining algorithms on a data set of 60,000 crash reports. For a baseline, we used a standard implementation of Stuco with equi-width binning with bin sizes of 3 and 10. We found that both baselines perform poorly when compared to CCSM, and this is especially true for larger bin widths. During our experimentation on production data, there were a number of cases where CCSM helped engineers resolve field crashes. For one severe group of crashes, engineers found a continuous contrast set indicating navigation to and from a module related to comments was the cause of this group of crashes. And so this insight surfaced by CCSM ended up being key to the fix for this issue. This crash is an example of an out-of-memory error, which is especially difficult to debug because we don't have stack traces. So this is a case where continuous contrast set mining enables us to analyze hard bugs due to its scalability to high-dimensional continuous data sets. So in conclusion, app crashes are severe symptoms of software errors with significant impact on software companies. We demonstrate that statistical pattern mining can surface anomalies to help developers resolve bugs, and we show that the analysis of continuous features further adds value to existing approaches. There is a growing body of research applying machine learning to crash triaging and resolution, and we believe that high-dimensional crash datasets continue to present interesting research opportunities in this space. Thank you.
Okay, thank you for your talk. Well, let's wait a question from the Slido. I have a simple question. Can you explain how did you categorize that? That means that clustering for clustering the out-of-memory crashes. I believe that the clustering can affect to the contrast set mining. So can you tell me that how did you cluster or categorize the crashes, and with what kinds of features do you choose?
Yeah, this is a great question. For the initial clusters, there are a number of ways that you can use to form the groups. So one example is using a hash-based categorizer. So this would be based on stack tree similarity. We have also experimented with k-means clustering, so that would create more fuzzy matches.
Mm-hmm. Great. And as you know that your research came from the industry, so the important question what I want to ask is that, do you have any plan to apply these techniques to real industry work? It means that of Facebook apps. Do you have any plans?
Yeah, so the data set that I mentioned that we evaluated on, these are all real world production crashes. So we gathered a data set of 60,000 crashes and ran this experiment for several weeks. So it is all using the production crashes and hoping to bring insight into problems that our engineers face. And we did work very closely with a lot of them. So we have demonstrated that this is useful for anywhere from 100,000 crashes to 1 million crashes.
Great. Can you anticipate that what kinds of errors, except the out of memory, this technique can be used for?
Yeah, so out of memory errors represents a very severe group of crashes for Facebook engineers to debug, and that's why we use that example for this presentation. But you can think of many data types that where a continuous compact representation can be very useful. So the navigation sequences is one, but you can create embeddings of many other features as well. And there are also naturally occurring continuous data sets in the real world. For example, the amount of time since the app has started, so process uptime. So time is a continuous feature, and this is something that you can use to analyze using continuous contrast set mining as well.
Okay, thank you for the impressive study. Thank you very much.
Well, thank you for listening.
Okay, let's move to the next one. Next presenter is Dr. Jinan Kim of Samsung Research. Hello, Jinan. It's your turn.
Hi. Okay. Okay. Can you see my presentation?
Yep.
Hi, this is Jinan Kim. Currently, I'm working at Samsung Research, and my role is developing some tools for developers. So in my presentation, I introduced the paper named Automatic Abnormal Log Detection by Analyzing Log History for Providing Debugging Insight. So this is context of my presentation. And first of all, let me explain why we did this research. As you all know, software is not only getting larger insights, but also increasing the complexity. According to a survey of software size, if all of Google's services are combined, it is said to be over 2 billion lines. Next, below two figures shows examples of software complexity. In the case of Tizen platform, developed mainly by Samsung, it is composed of various core components. So, and they are connected to each other. So it is often very difficult to analyze the root cause of defects. And the second figure shows an abstract architecture of SmartThings providing IoT device control service. Using SmartThings, you can control various devices through mobile, since the detailed communication logic between devices is very complicated. So it is also not easy to find which step generates abnormal situation. So in this situation, it is almost impossible to reproduce the defects. As a result, analyzing collected log is the only way to get a clue to solve the defects. However, the problem is that the more complex system, the more logs are left. And even most logs contains information that is not significantly related to the defect. To solve this problem, there are some various log analysis approaches. One of the most famous approaches is to define a certain key indicator in advance, extract in real time, and monitor whether there are some problems. This approach has chances in finding exceptional events, but it is not suitable for analyzing various test scenarios. Alternatively, there are some analysis approaches based on past test history. The right figure is the workflow of the paper published at ICSC in 2017, and it computes the pure similarity to recommend the most similar defects that occurred in the past. These approaches are good for covering various test scenarios, but needs improvement for precisely extract important log lines. So in our paper, we would like to introduce new log analysis approaches, combining advantages of the two approaches described above. We are calling our tool Historian in the sense that we use the test log history to analyze it. And the below figure shows the workflow of the Historian, but I skipped to explain details. From now on, I briefly explain how Historian computes statistics. Basically, we use the idea of TF-IDF, which is the popular algorithm in data mining. Simply explaining, TF computes the statistical value of how important a particular word in a particular document by counting occurrences, and IDF computes statistical value for how few occurrences of a specific word in a group of documents. Based on this idea, we consider each log line as a word. A set of log lines generated during a test scenario execution is as a document, and group entire log files as a document group. And then we compute importance and noise scores based on statistics. As TF is very trivial, I skip this and I explain some details of document frequency. And the left figure shows simple example of document frequency. Let us assume that we have 6 log files and we want to get important information for TC1 based on document frequency. It has 2 green log lines and 2 red log lines. Let's see the green line. It may not be important for TC1 as it also appears in other TCs. Conversely, since the red lines appears only in TC1, so it is highly likely containing important information for TC1. So it is the concept of document frequency. Basically, document frequency does not consider time information, so we propose a new document frequency concept by adding temporal perspective. That is whether a particular log line appeared mainly on specific date or not. If the existing concept of document frequency for test scenario is called TFS, then the new TF concept for time is called TFT, and we compute the overall noise probability based on 2 TF scores. Using this concept, Historian find abnormal log lines for given target log. More specifically, let P be the in% probability of line L and Pn be the noise probability of L for given TC S at time T. We find an anomalously presented and missing log line by using these formulas. First, as a high score of 1 minus P means that L is not usually occurred in S, and high 1 minus Pn means L is not noise. Therefore, L can be said to be an abnormal line containing important information that has not appeared in the past. On the other hand, high P means L is frequently occurred before in S, and high 1 minus Pn means L is not noise. Nevertheless, it is not occurred at this time. This indicate that L is an anomaly missing log lines. And this slide shows an example page of Historian. We provide actual log lines by highlighting anomalously appeared lines and anomalously missing lines. Next, I explain some experimental results of our paper. We plan the experiment by using Tizen platform, which is tested through a test tool called TCT. Among various test suites, we selected 3 tests as the experimental subject. Note that the third one is actively being developed compared with others and has a lot of network-related APIs. We first want to know how many lines are highlighted by Historian. To check this, we defined the metric named debugging import based on anomaly scores. Low D score means that developers only need to check small number of log lines and getting debugging site. This figure shows that the HTC shows, as you can see, the average DBT score is about only 0.04, and it means that developers only need to check only 4% of lines between 4 test pairs using by IR tool. And this shows some debugging effectiveness of our tool, and I skipped the test. And this means that when fail occurs, developers only need to check some abnormal log lines by using our tool. And actually, third figure shows that we have some problems in our algorithm, so we need to improve this. It's time to finish my presentation as I spent almost my time. So in our paper, we introduced a new log analysis approaches called historian. We use test history for finding abnormal log lines accorded by test logs. And okay, I finished my presentation. And thank you for seeing my presentation. Thank you. So
thank you very much. But you still have one more presentation time. Anyway,
yeah.
Let's collect the questions from the audience. Okay, the first question is, I'm confused as to why you need to find abnormal log lines for test output. Shouldn't a test fail to communicate the problem? Why do you need this for test logs?
Because there are a lot of tests during a day, and there are a lot of fails. And unfortunately, some platform logs, there are a lot of noises in the test log, so it is not easy to find important log lines. So we want to find some important log lines in advance to providing developers.
Mm-hmm. Okay, thank you. And next question is that, have you tried to apply these techniques to production system that is not for testing, for production?
Oh, actually, Tigen is used in various products in Samsung. For example, Tigen TV or some appliances. So I think that I applied our tool to the Tigen platform test, and it means that our tool is used for product platform.
Mm-hmm. You mean that the experimentation is not for toy problems?
Yeah.
Okay, thank you. And there is another question. Did you try to use the approach without considering the date? Essentially, it's the keep going on.
Actually, first of all, we do not consider the time, but then we only need to check the some log lines that appears in other test scenarios, but not this test scenario. So it means that we can miss some important information from the test. So yeah, I think that is not good for our test scenarios. Yeah.
Mm-hmm. And next one is it is the question what I wanted to ask too. How bad are the false alarms? Are they problem for users? Were they problems for users?
Oh, actually, currently I asked our research developers to check whether our highlighted log lines actually containing some important information for developers, and some of them say that it really contains important information, but some are not. So we check this information, and we need to improve to remove false alarms in the next time.
Mm-hmm. Okay, got it. And the last question from me, you don't have to answer about it. Do you have any plan to overcome the limitation what you thought? Historian may treat the abnormal logs as a normal one, so there may be a problem. Do you have any plans to overcome?
Oh, we have some plans, but actually we did not pick some details, not yet. Mm-hmm. So yeah, but yeah, okay.
I hope you may solve it.
Thank you.
Okay, thank you very much. Thank you for your talk.
Okay, thank you.
Okay, let's move to the next one. Next research will be introduced by Dr. Yoon Lin of National University of Singapore. Yoon, if you're ready, please start the talk.
Okay, thanks for introduction of Dr. King. Let me share my screen. Should be here. Yeah, can you see my screen?
Great.
Okay, so I'm going to start. Hi everyone, I'm Yunling. In this talk, I'm going to introduce our joint work on regression for localization. Regression bug is a bug introduced when programmers modify existing code. When we find a code does not work, there can be a huge number of changes made from the original working version. The challenge here is to locate the failure-inducing change. Here are the traditional problem settings for locating regression bug. We have a test T, an original program version P where T can pass, and a regression program version P prime where T can fail. We are going to find a set of changes from the total changes from between P and P prime, which can serve as the root cause. There has been a lot of regression photolocalization work to find the failure-inducing changes, including their debuggings and a symbolic-based approach. However, only reporting the failure-inducing change is still far from enough to help programmers to debug in a straightforward way. First, regressions can happen not only because the programs write something incorrect, it's also very likely that they miss some changes. In such a case, there's no straightforward failure-inducing change. Even with reported result, the programmers still need to investigate the code context themselves. Second, even the failure-inducing changes are reported correctly, the work is not done. Programmers still need to spend time to confirm the report and figure out the fix. In this work, we proposed a trace alignment-based approach, which compared execution trace on the regression and the original trace. Our approach can not only have state-of-the-art accuracy to locate the failure-inducing change, moreover, our approach can further explain the questions like why or why not a step happens and why the steps read the variables with incorrect values. The approach can be used in both an automated way or an interactive way. In the automated mode, the approach can report the failure-inducing change directly. In the interactive mode, our approach allows users to track the defects back to the root cause visually. Here is a screenshot of our tool, which is implemented as Eclipse plugin. In our tool, we list the regression trace in the left and the original trace in the right. When user clicked one step in either trace, our tool can automatically locate its correspondence in the other trace. Then the user can compare the aligned steps by the line of code and the corresponding read and return variable values. User can also provide feedback on the trace step to track the data control dependency along the trace so they can interactively narrow down the scope and gradually locate the root cause. Now let me introduce our approach. In our approach, we first record the execution trace of the original version and the regression version. Then we develop a trace alignment algorithm to align two traces. In this work, we're going to address two challenges in our algorithms. First, some program instructions or line of code can be repetitively visited in the trace because of loop iteration. We need to align those recurring steps in the trace. And second, we need to match traces with the equivalent semantics. And here is an example. The line 3 and line 4 changes quite a lot from the left version to the right version. Clearly, the static semantic has been changed significantly. At the line 3 and line 4 in the right is a loop, while they are actually conditional statements in the left. However, suppose they run both programs with the same input x equals to 0. In the first iteration of the for loop, the step 3 should be matched to step 3 prime, even if their ASD syntax is completely different. So should S4 and S4 prime. In our approach, we convert the trace into a tree and represented the execution trace tree generalizable enough to detect the equivalent trace semantics. An interested audience can check our paper for more details. After the trace is aligned, we can automatically ask while or while questions. If the steps reach a variable with the incorrect value, we will track its dynamic data dependency on the same trace In the meantime, we can find its corresponding step on the other trace and perform dynamic state dependency along the other trace. Those sliced steps serve as the answer for question why the steps read the variables with the incorrect value and why the corresponding steps on this trace reads the variables with the correct value. In the alignment mandings, we can locate an unexecuted. We can also record an unexecuted step in the root cause. In the case when the step cannot be aligned with any step on the original trace, we perform dynamic control dependency analysis to locate why the step cannot happen on the same trace. In the meantime, we search on the other trace for why its corresponding step does not happen on the other trace. In this example, we can automatically find there's additional return statement to change the control flow. And as a result, we can keep performing alignment slicing and mending until we stop. And these steps, those report steps are considered explanations, and the stop steps are the root cause. And we conduct an experiment on 24 real-world regressions, and our experiment on the 24 regressions show that our approach can outperform the baselines in terms of the reported accuracies, and we have much less false positive. Moreover, compared to the total trace size, the average trace size is about 64.1K steps, and the visit trace steps by our algorithms is only 13.1 steps. So the explanation size is much smaller than the total size. It is quite practical. In summary, we propose the trace alignment-based regression fault localization and explanation approach. It tracks the causality and propagates the defects back to the root cause. The experiment shows that our approach can locate the regression fault with state-of-the-art accuracy. Moreover, our tool is designed to explorable and interactive, which provides more flexibility for user to use in practice. This is all my talk, and I'm happy to have your question. Oh.
Thank you very much. Thank you for your presentation. It was really impressive. And as we don't have much time, I'd like to pick just one question. What is the runtime overhead while executing the test cases, and how expensive is the post trace alignment computation?
Okay, yeah, thanks for the great questions. I think the runtime overhead is always a problem of trace collections, and we in this work, when we are collecting the executions, they're actually 10 to 50 times slower than normal executions. But as for the debuggings, I think that is not so expensive for our tools because all the time traveling. So basically, recording replay techniques also called the time traveling debuggings, and it always incurs such overhead. And the accuracy for the slicing, mending, and the detection and slicing, mending, and alignment slicing, and mendings, and it is based on our observations quite accurate. And moreover, sometimes even if we have some inaccurate steps, our tool allows user to explore and compare both traces interactively, and they can have more intuitive context sense to understand where to fix the bug and what is really important, what is the root cause.
Okay, thank you. How about having the video chat after this session? I think please contact Yoon, and you may ask the questions for him.
Okay, thank you.
Thank you very much. Okay, let's move to the next. Mr. Ming Wen of Huazhong University of Science Technology will share his research to us. Ming, please start your talk.
Can you see my screen? Screen sharing?
Yes, exactly. Yes, great.
Okay. Good morning, everyone. My name is Ming Wen, and I'm from Huazhong University of Science and Technology. It is my great honor to present our journal first paper, Historical Spectrum-Based Photolocalization. And this is a joint work with the other 5 institutes. And we all know that spectrum-based photolocalization is a popular and important debugging technique, which can help developers to locate bugs automatically. It has also been widely incorporated in automated program repair techniques. However, it has to, the basic intuition is that those code entities covered by more failing test cases, but less passing ones are more likely to be the root cause of the bug. However, there are also two major limitations. The first is that the test coverage cannot reflect the root cause of the bug directly, and which is just a simply approximation of the bug. The second is that it suffers from the tie issue significantly, in which case the code entities in the same block cannot be well differentiated by existing techniques. Therefore, it motivates us to look for other information for better design of FL techniques. We all know that software evolves by means of code commits. And here we show a concrete example of the Apache Hadoop evolution history. And we can see that it receives plenty of commits per week. And those commits are checked into the system and to add new features, to fix the existing bugs, to perform refactoring tasks and so on. Besides, it might also introduce new bugs. We also observe that developers are often looking for the information of bug-inducing commits, as mentioned by the previous talk by Yun, that to debug in practice. They're looking for the commits that introduce the bug. Therefore, it motivates us to leverage such information to design FL techniques. Inspired by this, we further conducted a survey at Microsoft. And in total, we have received over 100 valid responses in total. And here we show the distributions for the developers with different years of working experiences. So our major findings is that over 75% of the developers agree that version histories are useful for debugging. And nearly 96% of them have ever leveraged the bug-inducing commits to locate bugs. However, unfortunately, 75% of them conduct such process manually due to the lack of tool support. Therefore, it motivates us to design an automated tool to help developers to perform the task of photolocalization. So motivated by these observations, we propose to construct the historical spectrum when performing the photolocalization task. Suppose VT is the target version for photolocalization. We first try to locate the change that introduced the bug, and we also identify the other changes that are irrelevant to this bug. And based on along the version history, we construct the historical spectrum, and we leverage the spectrum to perform the photolocalization. So our intuition is that those code entities modified by more bug-inducing changes, but less non-inducing changes are more likely to be the root cause of the bug. However, we have three major challenges. The first is that identifying bug-inducing changes from version history precisely is non-trivial. And the second is that we need to map the code entities from the inducing version to the target version. And the third is that the changes are usually tangled with other irrelevant code modifications and large in their sizes. Therefore, even if we have identified the inducing commits, it is still challenging to precisely locate the buggy statements. Here we've shown a concrete example. For the project Apache chart, the average size of the inducing changes is over 400 statements. However, the size of the corresponding fixing changes contains only less than 4 statements. Therefore, motivated by this, we propose historical spectrum-based photolocalization, and it mainly contains 3 steps. The first is that we identify the bug-inducing change. Specifically, we leverage program slicing techniques to minimize the testing logic and then perform binary search among the version histories. And then we construct the historical spectrum, which tracks the evolution of source code from the inducing version to the target version. And third, we rank all the suspicious statements by leveraging existing formulas such as Okaya, D-star, and so on. To evaluate the performance of our technique, we use the Defix4J benchmark. This is a widely used benchmark in the evaluation of FL techniques and automated program repair techniques. So it contains over 300 real software bugs. And the metrics we use is top N, MAP, and MR. So widely used in the evaluation of existing techniques. So in our first research question, we evaluate the effectiveness of HSFL, and we compare it to the traditional SPFL techniques. And here we can show that it is able to achieve an improvement of 28% and 40% for MAP and MR on average, compared with the state-of-the-art spectrum-based photolocalization techniques. And similar results have also been observed in terms of the top N metrics. And we can see that HSFL can significantly outperform the traditional spectrum-based techniques. So we all know besides spectrum-based photolocalization techniques, there are many other different families of different techniques. For example, the spectrum-based, mutation-based, slicing-based, and hybrid-based techniques. So we also compare HSFL with this kind of techniques. The major findings is that among all the baselines, the hybrid-based technique achieves optimal performance. However, our technique can also outperform the hybrid one with an improvement of 8% and 8% for MAP and MR respectively. So in our third research question, we integrate our HSFL technique into the learning to rank techniques. And here we show the results. And we can see that learning to rank techniques can outperform our technique and also the other families of baselines. However, after integrating our proposed HSFL as an individual feature to learning to rank techniques, the performance can be further improved by 3.7% and 5.4% in respect to MAP and MR respectively. So here comes to the end of our presentation, and all the data and this experiment and the source code can be found in the forum link, and questions are welcomed. Thanks.
Thank you very much for your talk. Okay, there is a question for your study.
Okay.
How do you filter out irrelevant changes included in fixes?
To determine whether it is irrelevant or relevant, we using testing. So we run the bug revealing test on the version histories, and we compare the variant signature and the stack traces, and to determine whether it is irrelevant or relevant. However, we cannot precisely determine whether it is the induced change or not. Okay.
Okay, thank you. Simple questions I have. As you mentioned that the finding bug inducing changes challenging task.
Yeah, it's very challenging.
I can imagine that there might be a case that the finding itself failed. For example, compiling test cases failed because of the target code changes. Did you meet that kinds of problems during your experiment? If so, yes. What kinds of decisions did you make?
Okay, yes, we have made such questions. Actually, during the experiments, we can only identify for the inducing changes for nearly 30 to 40% of the bugs. And for the other cases, we cannot precisely identify the change, but we can identify a regression range. So we can determine the range of the inducing commits. So therefore, we will leverage such regression range into our photolocalization techniques. So all the changes in that range, we will take into consideration and to prioritize and to perform tasks. Yeah.
Okay, thank you for your talk. Thank you very much.
Thank you very much. Thank you very much.
Thank you. Okay, let's move to the next. Next presenter is Professor Ivan of University of British Columbia. Ivan, please let us know your study.
All right, hello everybody. Can you see my screen okay?
Exactly, great.
Okay, super. Thank you everybody for joining me. Today I'll be talking about our work on visualizing distributed system executions with a group of lovely set of collaborators. So I don't think I need to convince everybody that distributed systems are really quite important because we're using one right now in order to communicate. And that's what makes ICSI happen this pandemic year. But of course, distributed systems are used for all sorts of things, including large-scale machine learning, all sorts of computation for delivering large files in a wide area, and so forth. Of course, the building distributed systems is actually riddled with many horrible stories, and there's stories of failures in large clouds. And a lot of that complexity in challenges in building distributed systems come from the fact that there's lots of race conditions, there's lots of non-determinisms, and of course, failures in the distributed setting. For coping with these numerous challenges, numerous techniques have been proposed, and a lot of these techniques come from both the software engineering community, but also the systems communities. And the ones that I'm going to focus on in this talk are log analysis, tracing, and visualization. And essentially, you can think of our work as combining these three topic areas. And so in our work, the perspective is to answer the question of why does my system behave in a particular way? It's a very broad, generic comprehension question, but you can make it much more concrete by asking, were two events concurrent, or did one event precede another event, for example? Or when there were multiple processes or nodes in the systems, did two of them communicate or did they not communicate? So these kinds of concrete questions are the kinds of things that lead to errors and are important to answer when you're debugging and trying to understand the distributed system. A common solution for answering these questions is log analysis. And you've heard several talks in this session already, where you can essentially run your system, collect the logs from the different nodes, and then study those logs, either in some textual way or in some other format. There's numerous challenges with log analysis, however. First of these is the scale. But in a distributed setting, you have new challenges that are much more apparent. So for example, if you have two events in two different log files, which event happened first? Actually, answering that question is quite tricky because it requires synchronization of timestamps and also requires potentially having virtual timestamps in order to order events reliably. So there's lots of challenges to a distributed setting. And in our research, we decided that one of the key issues is that people are missing the right tools. So people would be looking at logs as text, essentially, and trying to do text analysis, when in fact, the visual approach is much more relevant to this domain. And so what we present in this paper is essentially a set of tools. One umbrella of tools is for instrumentation of events in a distributed system, and these are called X-Vector. And X-Vector is a set of libraries for Java, C++, C, Go, lots of different languages are supported. And then the second tool is called Shiviz, and it's used for analyzing the logs that are produced by an X-Vector instrumented system. So the way X-Vector works is that it basically instruments the actual log statements in the system. And so your logs are now enriched with extra detail. And then Shiviz is used to look at those output logs and actually produce a happens before relationship, which is a partial order that looks like this diagram on the right. Both tools are open source. They're actually widely used. So welcome to you to try them out. So to actually explain this a little bit further, I'm not going to describe X-Vector, but I'll talk about Shiviz. And Shiviz is a tool that runs in a browser. And it kind of looks like this when you start it out. And I'll use an example log of a chord distributed hash table. As you can see, this log is rather long and rather complex. It has several nodes in it. And so the way Shiviz works is that it takes a regular expression to interpret this log and then to produce a visualization of this log. And here it is after a little bit of time. And so in this visualization, you can see that time goes from top to bottom. The boxes at the top of this visualization are the different nodes in my distributed system. And the different bubbles in the diagram represent different logged events. So for example, here's a logged event, here's another one at a different node. So one can think of Shiviz as trying to visualize a log by color coding it with the different processes that have executed each of the individual log lines. Shiviz is actually a suite of different techniques that are all integrated into this platform. So for example, I can search for text in my events. So for example, I can search for request, and then Shiviz is going to show me all the instances where this appears. I can also search for patterns of communication within this log. So for example, I can do a structured search and either draw the pattern here or search for a predefined structure. So for example, here I'm searching for a request response kind of structure. And so you can see that it's highlighting these structures in the actual log. You can also manipulate this diagram by, for example, clicking a node and trying to find all the other nodes in the system that have communicated with this one. And I can do this multiple times and find all the nodes that communicate with two nodes. So lots of different features are available within this tool. The last thing I want to show you is the fact that you can use Shiviz to look at executions, several executions together. So here I have a log with two executions, and I can switch between them, but they look very similar. But the best thing you could do with Shiviz is that you can actually look at them pairwise to understand how the logs may be similar or different. So that's a quick demo of Shiviz. So in our evaluation, we looked at evaluating both X-Vector and Shiviz. And so for X-Vector, we evaluated the performance and degradation that it has on the system. We found it to be rather reasonable. And evaluating Shiviz, we carried out several different user studies. I'm not going to go into details here, but I'll tell you that we have lots of evidence that shows that Shiviz actually helps people understand complex behavior in distributed settings. Moreover, Chevis has been used in several different projects, including the DB Sharp TLA Plus projects at Microsoft and the ACA actor-based framework. And by other researchers, including ourselves, we built several tools on top of the Chevis framework. So to conclude, this paper is about understanding behavior in distributed systems. The approach is to instrument the events in the distributed setting using libraries that are language specific, and then analyze them visually and present an interface to a person that helps them discover what happened in a distributed execution. Both tools are open source. We welcome you to try them out. Thank you very much for listening.
Thank you very much. Thank you for your talk. It was very interesting and practical research. Okay, there is a question, and it's exactly same as what I wanted to. Great talk. How scalable is Chevis? Considering in distributed systems, we can have millions of events, even in a short span of time.
That's right. Yeah, so Chevis, the X-Vector libraries that I've noted before, we've done scalability relative to number of clients and relative to number of messages. And we showed that it's actually reasonable for large distributed systems. The actual visualization engine itself is of course limited by the fact that it runs in browser. And so one way in which you can think of it is that we're betting on the fact that a lot of browsers are going to get much faster and will be able to use much faster technologies such as GPUs. But in practice, we found that Chevis scales to about 10,000, 15,000 log messages in order for it to be effective in a browser on a laptop, essentially. I think this is a problem for lots of visualization tools. We could take it out of the browser, but then it'd be much more difficult to deploy. So we've decided to prefer this deployability aspect of the tool and not be as scalable as a result.
Okay, thank you. And there are one more questions, but we don't have time. I think that you may open your video chat and invite them to get the questions about the information on the additional instrumentations and so on, and using the tool. I think that it is better to have a discussion and video chat by yourself.
Will do. Thank you.
Thank you very much. Okay, unfortunately, next turn is the last presentations of today's session. Today's last talk will be performed by Ms. Miao Zhang of City University of Hong Kong. Welcome, Miao. Please start your presentation.
Can you see my screen?
Great.
Okay. Hello everyone. I'm Miao from City University of Hong Kong. Today I will talk about an integration test order strategy to consider control counting. This is the outline of our talk. For interclass integration testing, a common problem is to determine the order in which classes are integrated and tested. Different test orders often lead to different test steps. A proper test order can significantly reduce the cost to construct these test steps. However, the existing measurement for stepping cost mainly involved interclass data copying, such as the number of method invocation, but it omitted control copying, which should also be considered. In Figure 1, Class A depends on Class B, and Class B depends on Class C. The relationship between Class A and Class C can be established through Class B. Such relationship is called transitive relationship. The object relation diagram is constructed in Figure 1b, where Figure 1c shows the object relation diagram constructed when considering interclass transitive relationships. But the solution generated by the same algorithm for the two situations are totally different. And considering control copying can help to avoid error-prone and expensive test steps. Therefore, we propose consider an integration test order strategy to consider control copying. Figure 2 shows its procedure, which improves the existing methods by adding the control copying when designing a new formula for stubing complexity. Our approach contains 3 steps. Firstly, transitive relationships are identified in the extended object relation diagram. Then control complexity is proposed to measure the stubing cost of control copying for a transitive relationship, which is based on the probability of the relationship's occurrence. Finally, control complexity is combined with the existing attribute complexity and method complexity to measure stubing cost. To evaluate the transitive relationships effects, we conduct experiments on 10 open source programs from SIR and answered the following 4 questions. We first determine whether transitive relationship exists in the actual programs. We count all transitive relationships containing 3 classes, such as class A's method A1 invokes class B's method B1, method B1 invokes class C's method C1. Figure 3 shows the percentage of transitive relationships in all relationships. Transitive relationships exist in all programs. And in 7 of 10 programs, the percentage of transitive relationships exceeds 40%. For the second question, we also set the list of transitive relationship chains as 4 and 5 respectively to study the impact of this setting on transitive relationships. Transitive relationship chains of like 3 already identify a large part of transitive relationships, with the lowest proportion as 66% for program log4j3 and the highest proportion 100% for JBoss. To evaluate the transitive relationships effects on the generated class integration test orders, we applied our previous proposed approach to generate class integration test orders under 2 situations. That is only considering direct relationship and considering both transitive relationship and the direct relationship. The results in Figure 5 shows that changes of test orders exist in all programs, especially in program log4j3. The test property of more than 46% of the classes differs in 2 test orders. Table 1 shows the stubing cost of test orders generated by considering a transitive relationship, which is lower than that generated by considering only a direct relationship for most programs. Therefore, we can conclude that control copying could indeed affect the stubing cost of a class integration test order. Consider more accurately assess the performance of class test orders and thereby generated the class test order with lower stubing cost. That's all. Thanks for your listening.
Thank you for your presentation. Okay, there are 2 questions. First of all, the figure 3. Is figure 3 based on method calls among classes?
Sorry,
Figure 3.
PS3?
Figure. The image that you used. Can you open the next page?
Next.
This is figure 1 and next.
I'm sorry. Can you repeat?
Okay, no problem. Okay, no problem. Let's move to the next questions, and I think that the audience will contact you at lobby. For next question is that for research question 4, The first research question is research question number 4. Yeah, is the stubing cost theoretically, or is it what developers had? How did you calculate that complexity? Stubing cost. Briefly saying, yeah.
You mean the stubing cost of the class test orders?
Did you calculate the stubing cost based on the overall complexity, and it is calculated from the all complexes? For example, A complex, M complex, and the T complex. Is it right? There is a formula in your paper.
The formula in my paper is the stubing cost. The stubing complexity is consisted with 3 parts. The attribute complexity and the method complexity has already proposed, and our study is proposed a new complexity called control complexity, and we use a linear weighted method to combine these 3 stubing complexity together.
Yeah. Yes, it is. Thank you. It is theoretical. Please contact her after this session. She will answer everything what you want to hear. Okay, thank you very much. Thank you for your presentation.
Thank you.
Okay, thank you. Okay, now it's time to wrap up. I appreciate all participants, presenters, audience, Zoomers, and OBSer. Thank you very much.